So the first problem asks for the radius of the curve. So I have my circle, I have radius, and I also have my givens on the side. So the first thing I decided to do was convert the kilometers per hour to meters per second, which I got 9.7 meters per second. Then I wrote a net force equation for the centripetal force with the force of friction acting on it, which I broke into the force of normal and also the coefficient of friction. And I have this free body diagram in the corner that showed me the force of normal is equal to the force of gravity. So I was able to substitute mass times the force of mass times acceleration due to gravity, and coefficient of friction in there is equal to the equation for centripetal force. And once I had coefficient of friction times the acceleration due to gravity equals velocity squared over r, I was able to substitute my values in and find the radius to be 17.5 meters. So here I have a little picture, I have free body diagram, and I broke up the normal force instead of the force of gravity on an incline because the acceleration is always going right to the center of the circle and not on a downward slope like in an incline problem. So I wrote out my net force equation, and what I found was I wanted a way to represent F and the x component of it without using Fn. So I started up here in the right corner, Fny equals Fg. And so Fny I was able to change into Fm cos theta equals mass times acceleration due to gravity. So from there I was able to divide both sides by cos theta and get that as a force of normal. And then I did Fnx equals Fn sine theta because it's opposite the theta in the free body diagram. And I was able to solve for Fnx to be mg tan theta because sine theta over cosine theta is tangent theta. So then I was able to plug in mg tan theta for Fnx, cancel out the masses, and I had g tan theta equals v squared over r. From there, I was able to multiply both sides by r to get rid of that denominator r, and I was able to just plug in the values for r, g, and v squared, and then just solve it like a regular equation. Once I got tan theta equals 0.5486, take inverse tangent on both sides, and I'm left with theta being 28.8 degrees. Alright, so this third part's a lot similar to the second part in that you have to find the force of normal and plug it back into the net force equation. But instead, now you have another force to worry about, which is the force of friction. And again, you break the two diagonal ones into their components. And you have the net force of y equals mass times acceleration y. And there's supposed to be no acceleration if the car wants to stay exactly on the ramp. So that becomes 0. And the force of normal y equals the force of gravity plus the force of friction y. I just moved over the force of gravity and the force of friction. In the beginning, it should be force of normal y minus force of gravity minus force of friction y, but I wanted to just move them over so everything was positive. And then you break the force of normal y into force of normal cosine theta. The force of gravity you can make into mass times acceleration due to gravity, and the force of friction you can make force of friction sine theta. And from here you want to move over the force of friction sine theta and break it into coefficient of friction and force of normal sine theta equals mass times acceleration due to gravity. And you want to take the force of normal using the distributive property out of both terms on the left side. Because from there you can divide both sides by cosine of theta minus sine theta, coefficient of friction, and you can solve for the force of normal. Then you go over to this net force equation, that's EFC equals MAC, and you have the force of normal x plus the force of friction x equals mv squared over r. Now, what we can do with this is write the force of normal x as the force of normal sine theta, and the force of friction x as the force of normal coefficient of friction cosine theta, and take the force of normal out of both these terms with the distributive property. And from here we can write the force of normal as mass times gravity over cosine of theta minus the coefficient of friction sine theta from what we solved for before, and this other term, and then we can multiply these two together and get what's down here on the bottom. And this is equal to mass times velocity squared over radius. And we can cancel out the masses, and then we have these two pretty big looking blocks of equation, but we actually have all the values we need. We can just plug in the theta, 28.8. We can plug in the radius, which is 17.5, and we could plug in acceleration due to gravity, which is 9.8. So when we evaluate this whole big block, we're left with just 15.45 equals v squared over 17.5. And you can multiply both sides by 17.5 and then take the square root of both sides, and you get 16.4 meters per second is the velocity.